Good morning, everyone, and thank you for having me. I'd like to discuss the notion of modeling workflow. Maybe I should mention that I'm a PhD candidate in the Department of Statistics. And I want to talk about this idea of a modeling workflow and what our experience has been with modeling the COVID-19 outbreak. The work I'm showing here is available first in the form of an article on the estimation of mortality, and this was in close collaboration with some epidemiologists in Switzerland. Our main point of contact has been Julien Rioux, who's really done awesome work. And then we also wrote a case study / tutorial where we get into some of the computational nitty-gritty. Finally, a lot of the work we've been doing has been through a software, a Bayesian Inference software called STAN, which was actually developed in Colombia. And I encourage everyone to check it out. So I'll first discuss what I mean by a modeling workflow. I'll show an example for a transmission model. I'll talk about the computational scaling and feasibility of such a model, and time allowing, I'll share some thoughts about how we can evaluate and expand these models. So Box, I think it was around the 70s or in the 80s, prescribed a certain scientific paradigm where we work through models in 3 stages. One, there's the building the model phase, where we're going to use our statistical expertise or our field expertise to construct the model. Then we're going to do inference on that model. And really what that means is learn about unknown variables and quantities in the model based on known quantities, so typically on data. And then we're going to criticize the model. And here the goal is not simply to validate or invalidate the model, but really to understand the shortcomings of our model so that we can then work on an improved model, right? Which is why once I reach the criticize step, I look back to the modeling, right? And I'll work with a new model, I'll do inference, I'll keep criticizing. And in the process, the hope is that this modeling exercise will give me an insight, whether that's explanatory or predictive, and that there'll be ways of applying some iterations of the model. And one of the takeaways, if we start thinking in terms of this workflow, is that we're not simply dealing with one model that we're fitting, we're actually dealing with multiple iterations of the model. And so rather than thinking about what are inference algorithms that support one particular model, I want to think about what are algorithms that are going to support this whole framework. And to illustrate that point, so Julien Rioux actually made all the code we used in that paper open source, including every iteration of the model, right? And each iteration is going to appear in a STAN file where you can really read and understand what's going on in the model. And you can see that here we're already looking at iteration number 15 of the model. And actually the one that got published was the 16th iteration. So we're really fitting more than one model. And that's where this idea of probabilistic programming comes into place. The ideal of probabilistic programming is that we're going to give practitioners an environment where they focus on the modeling, which is already very difficult, but the inference happens semi-automatically or under the hood, right? In particular, if you revise your model, you don't need to revise your inference because the probabilistic programming will take care of that. However, in practice, it's absolutely not true that you can ignore the inference algorithm. For one, you need to worry about having finite computational resources. The model you have may be very difficult to perform inference in. There are all sorts of pathologies that can arise. And you can't treat the inference as a black box, unfortunately. To some degree you can, but once you start getting to complicated and interesting models, that's less feasible. And again, to illustrate that point, so when Julien first reached out to our group at Columbia, which is the group led by Professor Andrew Gellman, he explained to us, this is the model I have, this is what I'm trying to do, and I'm working on model number 12. I'm almost done doing the inference. It takes 3 days to fit on the cluster. 3 days, right? So 3 days, okay, I can wait 3 days. But remember that this is model number 12. So if I have to fit, say 10 models and they each take 3 days, it takes 30 days to actually work through this modeling workflow. Right? And you can imagine how having to wait 3 days to fit the model really, really perturbs my workflow, either because I have to wait longer or because it can even discourage me from revising the model. And so quite fortunately, with a postdoc, Ben Bales, we looked at the model, we leveraged our understanding of the under-the-hood computation to reformulate the model mathematically. So it's the same model, it's just reformulated differently. And what we were able to do is take a model that takes 3.5 days to fit and get it to run in 2 hours. And the reason why that makes a big difference, again, is not because I can't wait 3 days to fit the right model, but I can't afford to wait 3 days for the wrong model to fit, so that then I can revise it, right? So with the 2 hours, I'm able to much more efficiently work through this workflow, and B, I can now add more complexity to my model, so that whatever I end up fitting in 3 days will be much more interesting. So that, I would say, was the main point of my presentation. And now maybe I want to go a little bit into some of the details. First of all, by discussing the model that we fitted, and it's an SEIR model. So I'm sure you've seen a lot of these during these symposiums. But I want to emphasize that there are 4 ingredients to that. One, it's the SEIR model. That's what I would call your mechanistic model for the disease transmission. The second ingredient is there's a forcing function that tries to model the confinement. And this, I think, we're doing an okay job at. We can certainly do a better job at. And 3, we're modeling the biases. And this is important because ingredients 1 and 2, to me, they're about modeling the phenomenon of interest. Now, once we get to ingredient number 3, we're modeling our probing mechanism. How is our data collected? What are the shortcomings in our collection of the data? What are the biases, right? And how does that add uncertainty to our estimations? And the 2 biases that we worried about were, 1, preferential assertment. So that's severe cases are the ones that tend to be tested and reported. And 2, delayed mortality. So if I look at 1 snapshot in time, what I'm going to see is so many reported cases, so many deaths. But amongst the reported cases, there are still a handful of individuals who will pass away. And the 4th ingredient, and that kind of ties into Bayesian inference, is that I can combine information from different data sources in the form of what we call a prior, and then use that to inform my analysis. Right? So I'm going to talk about ingredient number 1 and ingredient number 4 very quickly. So this is your SEIR model. Bon, there are a few twists, but to review what this does, we're splitting the population into homogeneous groups. And within one group, we imagine that people are affected by the disease in a certain way. So for example, they're infected and they're displaying symptoms. Or they've been exposed, but they're still incubating. Or they've recovered, right? That's what these compartments mean. And on top of that, we're going to split the population into different age groups because we know that different age groups react differently to the disease and also interact with one another differently. Right? And between these compartments, we're going to have flows. And this is very naturally described by a system of differential equation, right? So my statistical model at its core has a system of 62 coupled differential equations. And then on top of that, there are additional compartments to describe the probing mechanism, which is, what are the reported and the unreported cases. right? So we have this, something a bit more complicated in a linear regression. That's ingredient number one. And then ingredient number four is, when we're fitting such a complicated model, we want to try and pull as much information as we can, both from our data, but maybe from previous analyses. And one example of that, so we ended up using a different data source, but I'm going to talk about the Diamond Princess because I think pedagogically it's compelling. The Diamond Princess was a cruise boat where they identified a case of COVID-19. So the whole ship was quarantined. And then they proceeded to testing everybody on board, which usually in a regular population we don't do. We don't test everybody, right? So we had this snapshot where we're able to, estimate the average incubation period, and also what is the percentage of individuals that actually develop symptoms and don't develop symptoms. But of course, right, this is a population sample. It's finite, so there's uncertainty in this, and we're also aware that maybe it's not representative of what happens in a broader population. And the way we're going to incorporate this is through the form of a prior distribution. So instead of fixing, say, parameter psi, what I'm going to do is I'm going to assign a distribution of plausible values consistent with that analysis that accounts for the uncertainty, and that uncertainty then gets propagated into my final result. That's a very powerful way of pooling information. Okay. So scaling differential equation-based models. So we're doing Bayesian inference. I don't know how familiar most of the audience is with this, but the basic idea is to say, I have a model, I have some data, and I want to find the set of plausible parameter values consistent with my model and my data, right? So I'm not focusing on one value, I'm not focusing on the most likely value. I'm really trying to look at a host of possible scenarios, which of course is important to, amongst other things, to account for uncertainty. And this is going to be described by a posterior distribution, which is a formidable object to manipulate. And the way we try to understand this posterior distribution is by simulating samples. Right? We can do that with Markov chains Monte Carlo. In practice, when we're dealing with a high dimensional space, we want to use a class of sampling algorithms called Hamiltonian Monte Carlo algorithm. And very long story short, this is an MCLC algorithm that harnesses the gradient of the target distribution from which we simulate. But the problem is that now...
A 2-minute warning, Charles.
Perfect, thank you. Every time that I change my model, not only do I need to revise my target distribution, but I also need to revise the gradient. And that's a real burden for the user. Not to mention that if computing my distribution involves numerically solving a differential equation, well, how do you compute the gradient of that, right? And so lucky for us, we have a tool called automatic differentiation, which basically, based on the user's input to compute the target distribution, is going to break that into a sequence of operations, and then we can use the chain rule to do a sequence of Jacobian tangent products. And once we get to the ODE, so it turns out that the way you do this is you want to calculate so y being my solution and theta my input parameters, you want to calculate this Jacobian, and you can reformulate that as an additional differential equation. So what do I need to do? If k is the dimension of theta and n the dimension of the number of states in my ODE, it turns out I need to solve n plus nk differential equations, right? As opposed to just n. So that really tells you, what the computational scaling is. And if we're clever, we can try and reduce k, right? Which is basically what we did. We went from k equals 62 to k equals 5, which means we went from solving more than 3,000 states to solving less than 300. So I'll finish by saying that we are working on more clever approaches of solving this and implementing this in Stan. And I think that we can get something that has n plus k scaling as opposed to nk scaling. And that, if it works, as we hope it will, it'll be a game changer.